Something is amiss in our cognizance of the universe. Cosmology is drawing closer to a basic crossroads, wrestling with one of its most essential issues. How rapidly is the universe growing? For more than 10 years, two unique estimation techniques have been at odds. Observations of the present-day universe normally show that the pace of development, known as the Hubble constant, is around 9% faster than what is anticipated based on data from the early universe. Analysts had hoped that the James Webb Space Telescope, the most advanced telescope ever made, would help resolve this issue. However, consensus has yet to arise, as the telescope's novel and surprising observations have further highlighted the disparity, posing a potential challenge to the established cosmological model. Now, the need for new physics to either adjust or completely replace the 40-year-old theory is under serious discussion. A thrilling and fascinating possibility is that we are overlooking some aspect of the universe. Join us as we delve into how the new ultra-deep images from James Webb have recently confirmed that there is something truly flawed in our understanding of the universe. Our universe began with a bang, the Big Bang. Energy, mass, and space appeared instantly. From there, the young universe formed a growing plasma, a mixture of matter and antimatter particles that emerged and annihilated each other upon collision. Left unchecked, the matter and antimatter in this plasma would have destroyed each other completely. However, scientists believe an unknown imbalance allowed more matter to form than antimatter, thus saving the universe from immediate obliteration. Gravity then compressed this plasma, heating the matter so much that sound waves, known as baryon acoustic oscillations, traveled through the medium at roughly half the speed of light. Simultaneously, the dense energy content of the early universe expanded spacetime, pushing a small portion of matter safely away from the heat. As the universe expanded like a balloon, the standard story suggests that ordinary matter, which interacts with light, began to cluster around invisible dark matter, forming the first galaxies connected by a vast cosmic web. As the universe's objects spread out, its energy density and, by extension, its rate of expansion decreased. Yet, around 5 billion years ago, galaxies began receding faster, driven by the mysterious force known as dark energy. The most straightforward and widely accepted explanation for dark energy is that it functions as a cosmological constant, a uniform force that remains constant across both space and time, woven into the fabric of expanding spacetime. Named lambda by Einstein in his theory of general relativity, dark energy density stays the same as the universe grows, while the density of ordinary matter drops. Eventually, dark energy became the dominant contributor to the universe's expansion. When combined with ordinary matter and dark matter, the energy densities of these components set an upper limit on the universe's growth speed. These elements form the core of the lambda cold dark matter, lambda CDM, model, which describes the evolution of the universe and predicts its possible fate, an eventual heat death known as the Big Freeze. Many of this model's predictions have been proven highly accurate. However, this is where the trouble begins. Despite extensive research, astronomers are still puzzled about the true nature of dark matter and dark energy. As Afrolov, an astronomy professor at University College London involved with dark energy galaxy surveys, states, most scientists agree that the universe's current makeup is around 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing truth is that we still don't fully understand the latter two. An even greater challenge to the lambda CDM model is the growing issue known as the Hubble tension. Depending on the method used, measurements of the universe's growth rate yield conflicting results. The discrepancy is so significant that it has become a pressing issue in cosmology. Measurements derived from observing the early universe suggest it is expanding far faster than predicted by the lambda CDM model. These methods have undergone extensive testing and validation through numerous observations. As Nobel Prize-winning astrophysicist Adam Rees, who led the team responsible for the latest James Webb measurements, put it, the only explanation for the discrepancy between the two approaches is that our current model is likely missing something. Measuring the universe's expansion involves more than just using a radar gun. One of the primary methods to assess this rate examines the cosmic microwave background, CMB. The universe's first light, emitted around 380,000 years after the Big Bang, This imprint is visible across the entire sky and has been mapped to infer the Hubble constant with less than 1% uncertainty. Between 2009 and 2013, the European Space Agency's Planck satellite produced a detailed map of the CMB. In this cosmic snapshot, the universe appears nearly uniform, but slight variations in temperature mark regions where baryon acoustic oscillations left their imprint. By studying these waves, cosmologists deduced the amounts of ordinary matter, dark matter, and the cosmological constant, or dark energy, to calculate the Hubble constant, which came out to about 67 kilometers per second per megaparsec. The mysteries that the James Webb Space Telescope has begun to unveil are reshaping our understanding of the universe, challenging established theories, and inspiring new avenues of exploration. As the telescope continues to collect data, the implications extend across numerous domains of science and philosophy. One of the most pressing puzzles JWST is helping to address is the so-called Hubble tension, the discrepancy between measurements of the universe's expansion rate. On one hand, observations of the early universe, such as the cosmic microwave background, suggest a lower value for the Hubble constant. On the other hand, measurements of the local universe, including Cepheid variables and supernovae, indicate a higher value. JWST's precision and ability to observe faint and distant objects have provided new data that reinforce the higher expansion rate. This persistence of the tension suggests that our current cosmological model, the lambda cold dark matter model, may be incomplete or in need of revision. The telescope's findings are also shedding light on the enigmatic components of the universe: dark matter and dark energy. These two elements, which together constitute about 95% of the universe's total energy density, remain poorly understood. Dark matter's influence on the large-scale structure of the universe is evident, but its exact nature continues to elude scientists. JWST's observations of early galaxies challenge our understanding of how dark matter shapes the universe's structure. If galaxies in the early universe were more massive and developed than expected, this could imply that dark matter behaves differently than current models predict. The accelerated expansion of the universe, driven by dark energy, might not be uniform over time. Some cosmologists suggest that dark energy could evolve, altering the rate of expansion at different epochs. JWST's ability to probe distant galaxies offers a unique opportunity to test these theories. One of JWST's most surprising discoveries is the presence of massive, mature galaxies and supermassive black holes only a few 100 million years after the Big Bang. This challenges the standard timeline of galaxy formation, which posits that galaxies and their central black holes should take longer to grow to such sizes. These observations suggest that processes like star formation and metal enrichment may have occurred more rapidly in the early universe than previously thought. Supermassive black holes may have formed through mechanisms that are not yet understood, potentially involving exotic physics or interactions with dark matter. Beyond its contributions to cosmology, JWST is revolutionizing the study of exoplanets. By analyzing the atmospheres of distant planets, the telescope is searching for signs of habitability and even potential biosignatures. Its ability to detect molecules such as water vapor, carbon dioxide, and methane in exoplanet atmospheres is opening new doors in the search for life beyond Earth. The findings from JWST are not only advancing our understanding of the universe but also challenging fundamental assumptions in physics and cosmology. Questions about the nature of dark matter and dark energy, the mechanisms of galaxy formation, and the origins of life are pushing scientists to rethink established paradigms. These discoveries also raise profound philosophical questions about humanity's place in the cosmos. As we uncover more about the universe's origins and evolution, we are reminded of the vastness and complexity of the cosmos and the limits of our knowledge. As JWST continues its mission, it promises to deliver even more groundbreaking discoveries. Future observations will likely refine our measurements of the Hubble constant, provide deeper insights into the nature of dark matter and dark energy, and reveal more about the earliest epochs of the universe. The telescope's unprecedented capabilities ensure that it will remain at the forefront of astronomical research for years to come, serving as a bridge between current understanding and the uncharted realms of the cosmos. Whether by confirming existing theories or uncovering entirely new physics, JWST is poised to transform our view of the universe in ways we can only begin to imagine. The journey of discovery that the James Webb Space Telescope has embarked upon is not just a technical achievement, but a profound leap in humanity's quest to understand the cosmos. As it peers deeper into space and further back in time, JWST is providing a clearer picture of the universe's infancy, its large-scale structure, and the intricate processes that have shaped it over billions of years. The telescope's ability to detect faint light from distant galaxies is helping astronomers reconstruct the universe's timeline, revealing the formation of the first stars, galaxies, and black holes. One of the most significant aspects of JWST's mission is its ability to study the interplay between ordinary matter, and dark energy. These components collectively govern the evolution of the universe, yet their interactions remain poorly understood. JWST's observations are already challenging the prevailing lambda cold dark matter, lambda CDM model, which has served as the foundation of cosmology for decades. The detection of massive, mature galaxies in the early universe suggests that the processes governing galaxy formation may be more complex than previously believed. If these galaxies formed earlier and grew faster than predicted, it could imply that the role of dark matter in galaxy formation needs to be re-evaluated, or that other unknown factors are at play. The telescope is also shedding light on the mysterious nature of dark energy, the force driving the universe's accelerated expansion. Current theories treat dark energy as a cosmological constant, a uniform force that remains unchanged over time. However, JWST's data raises the possibility that dark energy might evolve, varying in strength throughout cosmic history. Such a discovery would have profound implications, not only for cosmology but also for fundamental physics, as it would necessitate modifications to Einstein's theory of general relativity or the introduction of entirely new physics. Another groundbreaking area of JWST's research lies in its exploration of exoplanets. The telescope's advanced instruments are capable of analyzing the atmospheres of planets orbiting distant stars, providing unprecedented insights into their chemical compositions. By detecting molecules such as water, carbon dioxide, and methane, JWST is helping scientists assess the potential habitability of these worlds. These studies are not just about finding life. They are also about understanding the conditions under which life might arise, evolve, and thrive in environments vastly different from our own. The search for biosignatures, chemical markers that indicate the presence of life, is one of the most exciting aspects of JWST's mission. If the telescope were to detect such signatures on an exoplanet, it would represent one of the most profound discoveries in human history, fundamentally altering our understanding of life's place in the universe. Even in the absence of direct evidence for life, JWST's findings are enriching our understanding of planetary systems and their diversity, offering clues about how common Earth-like conditions might be.